Okay, we get started. It's a great pleasure for me to introduce today's colloquium speaker, Reece from Harvard. In addition to being a great pleasure, it's somewhat of a challenge. How you do justice to a man of such a broad range of talents as Matt. Perhaps the easiest way is to point out that his time in Aspen this summer has been split evenly between the workshop on swampland and topography and the workshop for which I'm one of the co-organizers on the LHC collider physics, which are two relatively disparate areas of our field. So it's quite impressive that he's an active participant in both of them. Let me give you a little bit of the bio of Matt, his path through physics so far. So if I got this right, you got your PhD in Cornell in 2008, and then he went from there to do postdocs in Princeton and a short postdoc at Harvard before he was snapped up by Harvard and became a member of the faculty there. He's worked on many different areas of physics. I wrote them all down, so buckle up, it's a long list. No, I'm not going to do it all. He's trained as a model builder. He's worked on many aspects of model building, supersymmetry, extra dimensions, ADS-CFT, axion physics. He's worked on precision tests of the standard model, collider physics, the phenomenology at both the LHC and future colliders, dark matter. The list of future colliders is long, FCCE, muon collider, and things like that. He's also written papers on how dark matter might have killed the dinosaurs. I'm very excited to see, out of that long list of topics, what's going to show up in today's talk. So take it away, Matt.
Thank you. Let me turn on my mic there.
Okay. Is that working? You can hear me? Okay. No dinosaurs today, unfortunately, but I'm going to talk about colliders in context. The context isn't quite broad enough. Dinosaurs. This talk is going to give my perspective on oriented toward thinking about physics beyond the standard model, which is what I've been mostly thinking about over my career in different ways. On the questions of why we should be building more colliders and which colliders we should be building, so I'm going to be talking mostly about future colliders. I'll say a little bit about what past colliders have taught us. And the answers to these questions, the reason I said in context, is that I think we have to take into account the rest of what's happening in physics. So part of my talk is going to be about things that aren't colliders at all, but things like experiments that people whose focus is on atomic and molecular physics are doing to probe precision fundamental physics, or experiments that are looking for rare flavor-violating decays, for example, and how those things relate to what we might or might not be able to find at colliders. So the broader context of experiments, and also of our theoretical ideas of what is plausible and interesting. So I want to start out with kind of the big picture of where we are in particle physics. We have the standard model. The good thing about the standard model is that it fits basically all of particle physics. That's also the bad thing about the standard model. If you're trying to find something beyond it, it works frustratingly well. It does leave some puzzles, like we know neutrinos have mass. We don't know if they're Majorana or Dirac. That's a big, important question, which I will have nothing to say about today. Then there are bad things. There are things the standard model does not account for in the world around us. So things we actually know about our universe, like the fact that there is dark matter. Dark matter makes up most of the matter in our universe. The standard model does not contain a dark matter candidate. So that's a failure. We know that our universe began with some sort of scale invariant primordial density perturbations. They grew over time and became dark matter halos, and then galaxies formed inside those, and that's why we're here. Another reason why we're here is that there's matter around us and not antimatter. We didn't just annihilate away in the early universe, and the standard model doesn't explain either of those things. These are missing pieces. And then there are things that occupy a lot of the time of theorists like me, thinking about things that are not necessarily sharp problems with the standard model, but things that are just uncomfortable about it, things we don't like. And most of these are numbers that just seem bizarrely big or small. Like the cosmological constant, the accelerating expansion of the universe. It's a tiny number, we don't know why. The electroweak hierarchy, the scale of electroweak physics compared to gravitational physics. We don't know why that number is what it is. The strong CP phase, the fact that in low energy, strong interactions of hadrons, we don't see CP violation. That's mysterious. And then flavor, which I'm going to talk a bit about at some level later in the talk. We have several quarks and leptons in the standard model. Their masses span many orders of magnitude. Their mixing angles also span orders of magnitude. It's a weird structure. We don't know where it came from. We would like to know. Now, I orient a lot of my thinking in terms of thinking about energy scales and what we know and what we don't know. So electroweak physics is around 100 GeV. That's the scale of, say, the W boson, for instance, 80 GeV. The Higgs boson is 125. It's a little bit heavier. Everything below that, we have a pretty good theory of particle physics. We know that by the time we get to energies of 10 to the 18 GeV, gravity becomes important. That's just sort of dimensional analysis using Newton's constant. It puts out this energy scale when you throw in the right factors of h bar and c. In between here and here are 16 orders of magnitude. What can we say about what happens in between? Well, we have various constraints. LHC tells us, for instance, certain particles don't exist below a couple of TeV. Some of the precision physics I'm going to tell you about tells us that certain kinds of things don't happen below, say, 20 TeV. Higher you go, the murkier our knowledge gets. We know that inflation, if that's the right theory of the early universe, happened below this scale, somewhere around 10 to the 14. But we don't know how far below. It could be anywhere in many orders of magnitude here. We know that if a particle of an axion exists, its decay constant is bigger than this scale, but we don't know how much bigger. We have a few little bits of information, but they're mostly inequalities. Something is bigger or smaller than something. What would be really great is if we could have just one definite number somewhere in the middle to kind of anchor our thinking, but so far we don't. Sorry, one more comment I want to make here, which is just that as we talk about future colliders, what we're doing is sort of taking this line and moving it that way. Right? And one thing you might think is, well, it's really far away. We're not going to get all the way over to 10 to the 18. But if you think kind of on a log scale, there's sort of 15 orders of magnitude between here and here. Even removing one of them is a good step in the right direction. Okay, and before I start talking about the main part of my talk, I wanted to sort of summarize some recent things that happened in terms of planning in the field in general. There was something called the P5 process that happened a couple of years ago. Some people in this room were involved in this planning. And they had many recommendations. I can't tell you all of them, I won't have time, but one thing they recommended is that the United States should get involved in an offshore Higgs factory. Colliders like FCCEE and ILC, which I'll mention later, which are aimed at understanding the Higgs boson better, is one goal. Another thing they said is vigorous R&D toward a cost-effective 10 TeV PCM collider. PCM is kind of jargon, so that means parton center of mass. What that means is if you collide something like electrons and positrons, you're colliding, as far as we know, elementary particles. What you put in is what you get out. If you accelerate them to 10 TeV, you get 10 TeV is coming out. That's not what happens with protons. Protons are messy composite things. If you collide protons at 10 TeV, individual quarks or gluons inside those protons might be colliding at 100 GeV or 2 TeV. They're not getting all the way to the energy that you put in. So when they say PCM, they mean really the individual constituents should be colliding at that energy. And that's about an order of magnitude beyond where we are now. And they mentioned that could happen with various possibilities. I'm going to come back to those later. Now, just last week, there was a new report that came out from the National Academies of Science in the US. And they were tasked with a somewhat different goal. P5 was looking at kind of the next decade and making very concrete recommendations. National Academy's report is more like looking into the hazy future of several decades out and saying, where do we want to be? But their very first recommendation was that around the middle of the century, they would like to see the United States hosting the world's highest energy elementary particle collider. And that, again, is sort of this 10 TeV PCM benchmark that I'm going to come back to. They further mentioned that a muon collider R&D program might be the way to get there. They also said they would like to see the United States participate in the International Future Circular Collider Higgs Factory. That's FCCEE, currently under study at CERN to unravel the physics of the Higgs boson. That's basically the same thing that was one of the key P5 recommendations, except P5 left it a little bit more vague which Higgs factory we should get involved with. They made many other recommendations. I'm just quoting one more here. Because it's relevant to some of what I'm going to say later. They said we should continue to pursue basically a broad approach to neutrino physics, fundamental symmetries, dark matter, dark energy, inflation, the matter-antimatter asymmetry, all of these kind of big picture questions. Particle physics, this recommendation was less specific about how you get there, but some of what I'm going to talk about is related to these ideas of testing fundamental symmetries. And they made many more recommendations. It's an interesting report, both the P5 report and the National Academy's report. If you're at all curious about the future of particle physics, I think it's worth reading these things. But I wanted to highlight it just to show that I'm going to be kind of advocating for some things that are very similar to these recommendations that you're seeing here. These reports show that at least at some broad brush level, the kinds of things I'm going to tell you about are kind of consensus of the field of where we should be heading. Now, as I say colliders in context, I told you I'm going to talk about the context of other kinds of things like testing fundamental symmetries. One thing I'm not going to talk about today is the context of politics and funding, which obviously when you see these kinds of recommendations, this report was starting to be prepared a few years back. The world looks like a rather different place today than it did at that time. I don't feel like I have anything useful or insightful to say about that, but let's just move on. Okay. So collider physics basics. I want to talk about why colliders are important, what they've done for us in the past, and let me start with some history. The collider era in particle physics kind of goes back about 50 years. So if you start going back before the mid-70s, they were finding particles using cosmic rays. They were finding particles by doing fixed target experiments where you shoot a beam into sort of a stationary object. And even some of the key standard model discoveries in the 1970s were done that way. The charm quark was discovered at Brookhaven, shooting 30 GeV protons at a beryllium target. They didn't directly see the charm. They saw something we call the J-psi, which is a composite particle made of a charm and an anti-charm with a mass of about 3 GeV. Fermilab discovered the B quark in 1977, very similar. They discovered what we actually call the upsilon meson, which is a B and an anti-B bound together. But those were kind of the last discoveries of the old way of doing things, and then everything shifted to colliders. In fact, the charm quark was discovered simultaneously at Brookhaven and at SLAC at an E plus E minus collider called SPEAR. Very different kinds of experiments, but they both found a GeV J-psi particle. In fact, that's why we still to this day call it J-psi, because one experiment, Brookhaven, named it J, SLAC named it psi, and nobody wanted to settle the question of which one it should be, so it got stuck with both names. The reason why this shift from fixed target to colliders happened is just sort of a fact about special relativity. If you shoot a very high energy thing at a stationary thing and you work out what is the actual energy involved in the center of mass frame of the collision where they both have equal momentum coming at each other, it scales like the square root of the high energy you started with in the original frame. Whereas if you collide things, if they both have the same energy, that is the center of mass energy. The center of mass energy is twice the energy of each particle. You just add them together. And so colliders scale much better than fixed target. Of course, they're harder to build because you have to make the things actually hit each other. It's much easier to hit a big block of something than to hit a beam on a beam. But all the major discoveries of the standard model in the last 50 years have been done at colliders, with the exception of the B quark, the tau lepton also at SLAC, the W and Z anti-proton collider at CERN, top quark at Fermilab's PP bar collider in the mid-1990s. The LEP collider at CERN collided electrons and positrons. It did a lot of beautiful precision physics. It did not really discover any new particles, but kind of the closest I can get to telling you it discovered particles was it kind of confirmed that there are 3 generations of neutrinos in a fairly unambiguous way. And the LHC, the Large Hadron Collider, which is still operating today, 13 years ago, discovered the Higgs boson with a mass of 125 GeV. This was operating then at energies data. They had data at 7 and 8 TeV center of mass. Today it's operating at 13. But you can see there's been this steady progression from 3 GeV in the mid-1970s up to hundreds of GeV in the 1980s, a couple thousand GeV in the mid-1990s, up to several thousand, and now above 10,000 GeV. Okay, so there's been this steady upward march of energy over the decades. If you try to extrapolate this march, you might predict that we're going to be doing 100 TeV collisions in 10 or 20 years, and that is unfortunately not the case. So I want to talk about what the future colliders are that are planned, why they are further in the future, and why they're hard. Another thing to mention is that the SLAC experiment, this was a linear collider. All of the others since have been circular colliders. And so most of the proposed experiments today are circular colliders. There's a basic bit of physics, electrodynamics of relativistic particles you can work out. If you want to steer charged particles around the ring, you can use a magnetic field. And the momentum the particles will have is proportional to the magnetic field and the radius of the ring and the charge of the particle. Specifically, if you have magnetic fields of 10 Tesla, you're steering things around a ring of 100 kilometer circumference, and you just plug into this formula, you get out a momentum scale of 50 TeV. Just to make the dimensional analysis work, it's useful to know that a Tesla is 2 times 10 to the minus 16 GeV squared. Put that there because I can never remember what a Tesla is in units that are useful to me as a particle physicist, but that's what it works out to. Here's a picture of the LEP ring, which is also the LHC ring. The LEP was the E plus E minus collider that used to be CERN, and now the Large Hadron Collider, which collides protons, is there. It's a 27 kilometer circumference ring around Geneva. LEP collided electrons and positrons up to 104.5 GeV. If you're steering charged things around a ring, because they're going around a ring, they're accelerating inwards, and that acceleration makes charged particles radiate. So a thing that every circular collider has to contend with is synchrotron radiation, the fact that moving charged particles will emit electromagnetic radiation. How much do they emit? Well, it works out that when a particle goes one turn around the circle, it loses an amount of energy that's proportional to 1 over the radius of the circle, and the particle's energy divided by its mass raised to the 4th power. Low mass particles that you're bending around the ring emit way more energy than high mass particles, so this is particularly a problem for electrons. If you were to steer 125 GeV electrons around a 100 kilometer ring, which is the kind of thing the proposed colliders are proposing to do, they lose about 1 GeV per turn, a little more than a GeV. So you have to compensate for that. You have to have some sort of accelerators, so like some radio frequency cavities that are giving the particles a kick as they go around the ring, keep making up for that continual loss of energy. If you tried to put 500 GeV electrons around a 100 kilometer ring, you just wouldn't be able to do it. They wouldn't even be able to get around once before losing basically all the energy they had. On the other hand, tolerating the same sort of fractional energy loss delta E over E, you can see if I set delta E over E equal to a constant, then E cubed over m to the 4th is a constant. So, so the energy you could reach in a given size ring scales like the mass to the 4/3. Muon turns out to be about 200 times heavier than the electron. We're going to come back to that. That means you wouldn't have much of a synchrotron problem. You could accelerate muons around the 100 kilometer ring all the way up to 150 TeV without worrying about larger fractional loss of energy each time. You would have to worry about other things. It's not easy to build a 150 TeV muon collider. We talk about challenges. Anytime you're steering high energy particles around a ring, you need to worry about whether you have strong enough magnets, about the amount of power you're consuming, and all kinds of other things. Now, hadron colliders are, I've just sort of told you electrons have this weakness of synchrotron radiation. Hadron colliders have their own weaknesses, and the biggest one is that hadrons are a mess. And so a proton is not an elementary particle. We think of it as being made up of 2 up quarks and a down quark, but it's really more like a big bag of gluons and quarks and antiquarks, and when you smash them together, you get all kinds of junk out. This is an illustration of an LHC collision. This is actually one of the events that was involved in the Higgs discovery. It was a Higgs decay to 4 electrons. These kind of bars you see around the outside are signaling where the electrons are. But you can also see that there's just a big mess of other stuff going on in the middle. Most of it's relatively low energy and kind of easy to filter out, but it's telling you that hadrons are just intrinsically much harder to work with than electrons because they have all kinds of stuff inside. You're really interested in colliding individual particles. We call them partons, so maybe this gluon collided with that gluon with a very high energy. But at the same time, other lower energy stuff was spraying out of this collision environment. One way that we talk about that, that we quantify that, is what's called a parton distribution function, which is just as a function of the fraction of energy of the proton, how much energy does an individual particle inside have? So for instance, this is showing you basically the probability of a quark carrying, or the sort of distribution of how much momentum the quark tends to carry. So valence up and down quarks tend to carry kind of 10% of the, order 10% of the energy of the proton. It's like gluons and anti-up quarks and anti-down quarks and strange quarks and so on tend to carry smaller amounts. And as a consequence, if you collide protons and you start looking for particles that come out of the collision, you usually don't have sensitivity to them all the way up to the energy of your collider. So even though the LHC is colliding at a center of mass energy of 13 TeV, you might think if you're making pairs of particles, you can divide that by 2. You can rule things out all the way up to 6.5 TeV, but then you look, even for pretty strongly interacting things, this is a gluino, which is something that's a super partner of the gluon. It's one of the more strongly interacting things you could imagine making in the LHC, and it's only ruled out up to 2 TeV. I mean, that's still a pretty interesting bound, but it's not half the energy of the collider. And that's because things that are colliding to make these gluinos are carrying only a fraction of what you saw. Okay, so that was a little bit of sort of the big picture of how different kinds of colliders work. Now I want to talk about some of the possible futures. The LHC is colliding protons, as I've said, at about 13 TeV. It's a 27-kilometer circumference ring, and it's using 8 Tesla magnets. So you can ask, how can we do better? And what I've told you so far, you can already think of several ways you could do better. If the momentum you can achieve steering things around a circle is proportional to the magnetic field and the radius, well, obviously one thing you could do is make the radius bigger or make the magnetic field bigger. That'll help you get to higher energies. Proposed colliders use rings up to about 100 kilometers, so that could multiply your energy reach by 4. You can have stronger magnets, and proposed colliders use magnets up to 20 Tesla, which would give you 2.5 times the energy reach. The problem is that these 20 Tesla magnets don't exist. So people have proposed colliders that may use them, but there's a lot of technology development that needs to be done before you get there. You can avoid all the messiness of hadron collisions by colliding leptons. These are electrons or muons. There are a couple of different ways people propose to do that. One is to use lower energy leptons, but focus on them being cleaner and try to do more precision physics. So don't really go for higher energy, just try to do more precise measurements. The other is to try to gain from higher energies. There, you can collide electrons at 13.6 TeV. You would get nearly 10 times the energy reach you do by colliding protons because you're colliding elementary particles instead of colliding messy things and only having a small fraction of the energy be in the protons inside. If you want to collide leptons, you've got to avoid the synchrotron radiation problem, and there are basically 2 ways people have proposed to do that. One is to go to a linear electron collider. So you're not going around a circle, you're not accelerating. The other is to have a circular muon collider. I'll talk more about muons in a moment. First, I want to talk about the proposed precision colliders. So these are what we call Higgs factories, and you saw both the P5 and the national academies recommended that the US get involved in these experiments. What a Higgs factory does is to collide electrons and positrons at an energy of about 240 GeV. That's way below the LHC energy. So you're not going to make new heavy particles that you wouldn't have seen at the LHC. But what you can do is make a lot of Higgs bosons. This is where the cross-section for this process called Higgs-Strahlung, where your E plus E minus goes to ZH, maximized. And it's reasonable to run such a collider at an intensity that would generate around 1 million Higgs bosons. That's not actually really more than the LHC is generating, but it's a much cleaner environment to study them in. And so you can, for instance, you can basically just count how many of these events do you have, 1 over the square root, and that tells you how accurately you measure this interaction strength. You get kind of a 10 to the minus 3 measurement of this interaction strength immediately. And if you measure all the different things the Higgs actually does when it comes out, all the different ways it decays, you can measure lots of other Higgs interactions to percent level accuracy. So you would get a nice, precise kind of blueprint of what the Higgs is and what it does. These proposed colliders would not just be Higgs factories. They would also run at a center of mass energy where they can just resonantly make Z bosons. That's what LEP did in the 90s. But LEP made 10 to the 7 Zs, and some of these experiments are talking about making as many as 10 to the 12. You can just do much more precise Z boson physics than people did 30 years ago. Maybe you could also run at, say, 350 GeV, where you can make a top quark and an anti-top quark and study the properties of the top quark more precisely than you can do in a hadron collider. These experiments are all about precision. And there are 3 of them that are worth mentioning, I think. FCC-EE at CERN. The FCC stands for Future Circular Collider, EE because it's electron-positron. This would be planned to happen after the LHC finishes running, which is going to keep going for a while, another nearly 15 years of LHC physics. There is an ongoing European strategy process in particle physics, so we'll see if they sort of maintain this plan as it is, but that's sort of the state of things now. This would be a 91-kilometer tunnel, which is basically the biggest tunnel you can possibly build near CERN without running into mountains or some other obstruction that prevents you from going larger. And this would be running at the Z, it'd be running in Higgs factory mode and running to make tunnels. There's a very similar plan from China called CEPC, Circular Electron Positron Collider. Maybe the only difference worth noting as far as physics is they are less certain about wanting to do a TT bar run, I think, but they've talked about it as a possible upgrade. And if this happens, currently the rumors seem to be that it would be in Henan province. The capital is Zhengzhou. It's about 2 hours by train from Beijing. We will probably find out later this year if this is going to happen or not. There's another 5-year plan coming from the Chinese government. I hear sort of positive murmurs, but I can't say if we should expect this to happen or not. Then there's the International Linear Collider in Japan. This one's different because it's not circular, it's linear. That means in principle you can keep making it longer and go to higher energies because you don't lose proton radiation. This one has been discussed for the longest time. It's the furthest in planning. There's a site that's chosen. Sort of everything is ready to start building it, except money. And at the moment, it seems to me like this is unlikely to ever happen. But at some point, the Japanese government sort of said, everything is in place, we can do this, but we need the international community to come forward and pay a big part of it. And that has not happened. Hadron colliders. There are 2 of these that are relatively concrete in their planning. Both of them are planned to follow a Higgs factory. So they would, similarly to how LHC lives in the same tunnel that LEP did, these would work in the same tunnel as either FCC-EE or CEPC. So these are FCC-HH at CERN, SPPC in China. FCC-HH started out aiming for 100 TeV, and then they sort of scaled back. So now they're talking about 14 Tesla magnets and 84 TeV proton collisions. You could even scale down the magnets and think about lower energies, but maybe getting there sooner. So they're a little pessimistic about magnets, is my sense. Whereas SPPC, if you read their planning documents, they say by mid-century, we're going to have 20 Tesla magnets, and we can get to 125 TeV proton collisions. The reason is they're thinking about iron-based high-TC superconducting magnets. So very similar physics, kind of a moderate different level of optimism about how far you can go. It really all hinges on the magnets. And let me say, this is not just having big magnets. Of course, big magnets exist in the world, but you need lots of them. You need high field quality, you need reproducibility, low energy consumption, and low enough cost to have many of them around the ring. So this is not just someone somewhere needs to make a 20 Tesla magnet. This is like you need to have really high quality 20 Tesla magnets reliably. And that's the hard part. Some other kind of wackier ideas. So all the things I've just said are either E plus E minus or proton-proton colliders. They're like ones we already have, they're just bigger. Qualitatively different things you can do. You can collide muons. I'm going to talk about that in a fair amount of detail, so let me not say a lot more now, except to say that there's another proposal called mu-Tristan out of Japan, where there's a lab called JPARC doing a muon experiment that already has low emittance, positively charged muon beams, but not negatively charged muons. And so what some people have proposed there is, well, let's not try to do a mu plus mu minus collider, but instead let's try to collide positively charged muons on electrons, or positively charged muons on other positively charged muons at 350 GeV in the first case, or 2 TeV in the second. Another idea that's sort of a perennial thing that you hear about is plasma wake field. This is accelerator technology that's much more compact. So conventional radio frequency cavities accelerate things maybe 100 megavolts over a meter. Plasma wake field accelerators might be more like 10 gigavolts over a meter. You can imagine drastically shrinking how big a linear collider has to be if you can use this technology. There are many technological hurdles that have to be overcome. People have talked about it maybe being easier to generate electron-electron collisions than electron-positron collisions. And if you do any of these things, mu plus E minus, mu plus mu plus, E minus E minus, these are not particles and antiparticles, they don't annihilate. So to get interesting physics out of it, you might have to rely on these particles radiating other particles. And we're going to talk about similar physics at muon colliders in a moment. So that's kind of the landscape of all the things we might do. I want to spend some time with muon colliders because it's gotten a lot of attention recently. I think it's a very, from the point of view of a theorist, there are a lot of things about it that are very appealing, but it also has a lot of experimental challenges. So I want to sort of give you the picture of the good and the bad. The muon is just like the electron, but heavier. It's 200 times heavier than the electron. It's about 1/10 as heavy as a proton. It decays, much like the neutron. This is basically like a beta decay. Decays to an electron antineutrino, and a muon neutrino in about 2.2 microseconds. And we say this process preserves lepton flavor. I'm mentioning this because I'm going to come back to it later. We have a muon coming in, but we have a kind of neutrino coming out that carries sort of a muon quantum number. We make an electron, but we also have an antineutrino coming out that has kind of the opposite of the electron quantum number. And so this thing preserves a symmetry in which you can count muon number and you can count electron number, and they're both preserved. We're going to talk later about things that don't do that. We know these are not actual conserved quantum numbers in the world around us because the different kinds of neutrinos can turn into each other. But that happens at a very low rate. So for most practical purposes, we can forget about it and think of these as basically conserved quantum numbers. Okay, so muons are appealing because they're basically electrons without the synchrotron radiation problem. You think electrons are great because they're elementary particles, we like to collide them, we just can't get them to high enough energies. Muons avoid that, but they have a lot of challenges. Accelerator physics challenges, how do you get the muons in your collider in the first place? Collider physics challenges, how do you build a detector in this environment? Kind of laboratory and environmental safety challenges of how do you avoid radiation posing a danger to people. And all of these are basically because the muon doesn't live very long. At rest, it lives 2.2 microseconds. So the first problem is how do you get a beam? It's easy to get muons. You just smash protons into a target that makes pions. Pions decay to muons. But when you do that, you get a big spread of muons with different momenta. They're not a nice collimated beam that you can steer around the ring. The main proposal for how to do this is called ionization cooling. The idea is you pass muons through some material. As the muons pass through, they're ionizing the material around them and they're losing energy. And then you put them through an RF cavity that accelerates them, but it gives them more momentum only in one direction. Okay, so they're losing momentum kind of three-dimensionally inside the absorber. They're getting a kick in one direction, then they're losing it again, then they're getting a kick. And there are also magnets that are helping to focus them and keep the beam relatively small. The principles here are 40 years old. The practice barely exists. There's been one experiment called MICE, the muon ionization cooling experiment, that demonstrated that some elements of this work the way you expect them to. But that's very far from having it work on the scale that you need to actually build a useful collider. So that's one of the major problems. The kind of thing people are talking about with the muon collider is something like a 10 TeV collider with a circumference of about 30 kilometers. That's sort of roughly the size of Fermilab. Once you get the muons up to 10 TeV, you're no longer quite so worried about them decaying, and they can live a fraction of a second. They can travel thousands of times around this ring at the speed of light before they decay, but they are still decaying. So whenever you have a muon beam, you want to have a lot of muons in your beam, you're going to have a lot of radiation coming out of it. And you might think, well, this radiation is electrons, which are going to get stopped in whatever they hit, and neutrinos, which are mostly harmless, but at these high neutrinos are not so harmless. They're going to interact with material, they're going to produce showers that contain additional things like charged particles, and those are dangerous. So the problem is, how do you build this thing without someone sitting in a basement in suburban Chicago getting an unhealthy dose of radiation? And there are various ideas about how to do that. One is to minimize straight segments of the ring. The longer a straight segment, sort of the more path there is to have things decaying in that particular direction. If it's really perfectly circular, you're sort of evenly spreading the radiation out in many directions. Making the ring deeper underground helps. Wobbling the beam, making it sort of point slightly different directions at different times so that no one place is getting the whole dose helps. There are ideas, but that's one of the practical issues. Another issue for building an experiment is that these decay products that come out of the muon decays can smash into your accelerator components and into your detector and make it hard to tell what's going on in your actual collision event because you just have this flood of decay particles coming in. And the way people propose to deal with that is to have these blue tungsten nozzles inside the detector. So the rest of this is different detector components, trackers and calorimeters and the usual things you find at a collider. But these blue nozzles are basically just there to absorb stuff. Make sure that it doesn't get into your detector. It would be pretty good at that. It would remove a large fraction of this beam-induced background, but they wouldn't remove all of it. Basically, these nozzles would be glowing. They would be emitting low-energy stuff into the detector. And it's a challenge, but experimentalists have faced, at least from my perspective as a theorist, things that look kind of like qualitatively similar challenges, like pile-up at high-luminosity hadron colliders. You have just a lot of low-energy stuff in your detector, and you're trying to separate it out from the high-energy stuff that you're interested in. One thing about this that's difficult is that the nozzle design as it stands would limit access to small angle physics, so you just don't detect things in this region. We did have a talk on Tuesday about ideas of how you might try to improve on that, but that at least is a potential limitation to what you can do. Let's see, let me not linger on this slide because it's making a point I kind of already made, which is just that because muons are elementary particles, a given muon collider is roughly like a higher energy proton collider where you're only getting a fraction of the energy in a given collision. Another qualitative thing I want to say about muon colliders, I just told you you can use all the energy of the collision, but actually one of the great things about them is that you don't always do that. Muons also radiate photons and Ws and Z bosons, and those can collide too. They carry only a fraction of the initial energy, but they can give you important collisions. And in fact, annihilation processes that involve the mu plus mu minus always have amplitudes that scale like an S-channel pole. They go like 1 over the energy squared of your collider, whereas these other things can collide in ways that don't have that suppression. And so if you pick a physics process like production of top and antitop, the solid line is making it through these photons and Ws and Zs that you radiate. The dashed line is making it directly from mu plus mu minus. You see the gauge boson collisions actually win collider energies above about 4 TeV. Higgs production, you're basically winning from the beginning, colliding gauge bosons instead of colliding muons. That coupling is tiny. So you should really think that muon colliders can be used as gauge boson colliders. That's getting away from making them analogous to electron-positron colliders in some ways, at least the ways we've used electron-positron colliders in the past. And I'll also mention one of the participants in this program, Kaping Xie, is one of the people who really worked a lot of this stuff out several years ago. Okay, so that was a quick kind of tour of different kinds of new colliders. And now I want to switch gears and talk about precision. There's this paradigm of effective field theory that we use a lot in particle physics, where we think about having some sort of heavy particles or heavy fields. Here I've written down two fields, psi, which has a small mass, and phi, which has a big mass, and they interact with each other. And if you're at energies above the mass of phi, and you need to know about both particles, and you study scattering processes where you explicitly think about the heavy particle, and you have amplitudes that at high enough energy don't care what the masses are. If you go below the mass of the heavy particle, you can do experiments that involve psi. You don't have direct access to phi, and it's better just not to talk about phi at all. So we do what we call integrating it out. We get some effective theory. We write down a 4 psi interaction, and that represents the exchange of the heavy phi that we don't know about. And these things have matrix elements that grow with energy. They go like E squared over big M squared, the mass of the heavy particle. So if we know the UV physics and we want to know that we want to work with IR physics, this procedure is very well defined and useful. But when we're thinking about looking for physics beyond the standard model, we're more in the other position. We know the low energy physics, and we want to look for things that are high energy. And one way to do that is to look for effects that are growing with energy. To look for things that scale like this. That's what basically all precision collider physics processes are at some level doing that. They're looking for things that scale like inverse powers of heavy physics. One reason that's pointing to new physics is quantum mechanics tells us that amplitudes can't get too big just because of unitarity. S matrix is a unitary matrix. The elements can't be too big. If I wanted to do this rigorously, I would go to angular momentum basis and tell you about partial wave amplitudes, but roughly this is what you learn. And that tells you that if you see amplitudes growing with energy, there's got to be some new physics out there. The problem is that you don't know what it is. Maybe it's the thing I showed you before. There's this particle phi, and it's just being exchanged. Or maybe it's something more like this. There are two different particles involved, and they run in a loop. All you see is the low energy thing growing with energy. You don't know which one of these is right. Precision can tell you that something is out there, but it can't tell you what it is. That's a challenging inverse problem. And in general, it's very hard to get enough information to solve it without going to high enough energies to just directly see that, oh, the heavy particle is there. So I say this because I want to make maybe a slightly polemical point about Higgs factories, which is that Higgs factories give you this beautiful list of what the Higgs can do with percent level accuracy, or even better than percent in some cases. But if your new physics effects are scaling like 1 over some heavy mass squared, and you're doing measurements at the percent level, then roughly you're only going to learn about masses that are a factor of 10 above what you already know. And so Higgs factories roughly can tell you about things with a mass at a TeV. But the LHC already exists. It can directly make things with a mass at a TeV. So, for example, I can look at this hypothetical particle, the superpartner of a top quark. This is a plot that Gigi Fan and I made 10 years ago. There are probably more updated versions of it, but what it's showing you is precision Z physics of an E plus E minus collider gives you this orange exclusion, which basically rules out things in the kind of 700 to 800 GeV range. Precision Higgs physics gives you this purple curve, which you have two of these particles with equal mass. It's ruling them out up to something like 1 TeV. Then you can ask, what did the LHC already tell us? Well, it told us these particles are ruled out up to 1.2 TeV. Although there are some areas up here that it didn't cover. There are always some corners and crannies and loopholes that can hide from LHC searches that you could cleanly rule out with lepton colliders. But you're not getting a qualitative leap to a new energy regime that you're not already probing. So Higgs factories, they do beautiful, beautiful precision physics. But if you're searching for physics beyond the standard model, they're not a leap ahead of the LHC. Conversely, things like high energy colliders, like a 10 TeV muon collider, for example, we think of them as direct search factories. You look for heavy things, you just directly make the particles. They can also do some interesting precision physics. So for example, you can do Higgs physics without looking for the Higgs. This is an idea some theorists called Higgs without Higgs a few years ago. And the idea is that in the standard model, the Higgs boson couples in a way that it didn't have exactly the interactions it has in the standard model. You'd have amplitudes that grow with energy. As I've told you, that's always a signal that there's some other new physics at higher scales. Higgs couplings are exactly such that they cancel all of those things that grow. But that means that the Higgs couplings were a little bit different than in the standard model. Then you have things that grow with energy. And the best way to look for things that grow with energy is just to go to high energy. So instead of just making lots of Higgses and measuring their properties directly, you can just look at something like this process, WW to TT bar. You're not directly seeing the Higgs, but it's there in a virtual way. If it's not doing what it should, you will see this amplitude grow with energy. And so you can hunt for those deviations. This is work that some of us did for a document called the Muon Smashers Guide, making the case for a muon collider several years ago, and then it was recently revisited by Jen Liu and collaborators. And they made this nice plot showing that the accuracy you would get on the Higgs coupling to the top quark at a muon collider by doing this kind of thing is actually better than the accuracy you would get at Higgs factors similar on the same coupling. Okay, so this is to make a bit of a polemical point that some of the case for doing Higgs factory physics can actually be done better at a high energy collider, and much of what the Higgs factories can cover has already been covered by LHC. That's sort of a limitation of trying to do precision. You also see that with low energy precision experiments. So for example, the muon G-2 experiment has measured this interaction to many decimal places. It's a remarkable experimental achievement, but it took basically 20 years to figure out if it was telling us that there was something new there or not. The current latest standard model estimate agrees with the experiment. It's a beautiful example of both theory and experiment going to super high precision and telling you you understand the theory really well. But it's extraordinarily hard to make a convincing discovery in this way. To really show people, I measured this precisely, and I understand my theory precisely, and I know how to compare them. I can convince you that there's something there. That's a hard thing to do. The place where it's easier to do precision physics is if you're looking for something that the standard model predicts to be 0 for practical purposes. And that's what a lot of experiments looking for CP symmetry violation or flavor violation are doing. They have very good approximate symmetries of the standard model. You look for something that should be 0, and if you see that it's non-zero, you kind of immediately know you've found something new. You don't have to worry about whether you've got the 6th decimal place of some number right. You just know you saw something new. So I want to talk a little bit about some of these experiments. Electric dipole moments are something that violate CP, or equivalently they violate time reversal. These are terms in the Hamiltonian that involve a spin dotted into an electric field. If you think about having a spin in an electric field and playing the video backwards, the electric field points the same way, the particle spins the opposite way, so the spin flips sign. So this is a time reversal odd term in the Hamiltonian. In the standard model, time reversal violating effects are very, very small. We don't really know why they're very small, but it's an empirical fact that they're very small. So that means that if you can measure such things, you can easily look for physics beyond the standard model. And currently, the best limit on the electric dipole moment of the electron comes from an experiment not that far from here at Gila in Boulder. led by Junia and Eric Cornell. And what they do is they trap molecular ions, hafnium fluoride, in a trap. They do precision spectroscopy, and there are several different states of this ion where the electron spin is pointing in different ways relative to the axis of the molecule. And what having these different states lets you do is various systematic controls where you flip the sign of your applied magnetic field or your applied electric field, and the different states shift in different ways, and you can cancel out a lot of systematics. They can do this beautiful experiment, and they show that the electron EDM is smaller than 10 to the minus 30 e centimeters. So e is the charge of the electron. Remember, the size of a proton is about 10 to the minus 13 centimeters. This is saying if the electron, if you think of it like a little dipole, it's smaller than 10 to the minus 17 of the size of a proton. It's an amazingly precise experiment. And there are lots of ideas for how to go further with this kind of thing. So that was the electron electric dipole moment. You can also think about electric dipole moments of quarks. You can think about what's called the chromo-electric dipole moment of quarks, which is a similar thing, but with the gluon interaction instead of the electromagnetic field interaction. And the theory story here is harder because we don't have direct access to quarks. You have to embed them inside a nucleus. But there is a story about how to go from corrections to the standard model like this to corrections to nuclear physics. And what people have argued is that there's a certain class of nuclei. They're called octupole deformed nuclei, and they're sort of shaped like a pear, that have large intrinsic sensitivity to CP violation. These nuclei are radioactive. One of them is radium-225. There's thinking that protactinium-229 might be the most sensitive of these, but nobody yet knows how to work with it well enough to do experiments with it. But there's a lot of activity in trying to measure time reversal violation or CP violation in these systems, and it's extremely sensitive to physics beyond the standard model. There are many people doing this. Just to mention a few people I know in the Boston area, Ronald Garcia Ruiz at MIT and John Doyle and Shane Fan at Harvard are all pursuing ideas along those lines. And there are plans. Again, you have to sort of take this with a grain of salt because this is extrapolating 10 to 15 years in the future, but there are plans to improve electron EDM bounds by a few orders of magnitude. Neutron EDM bounds, similarly, these radioactive molecules would be going into similar territory as this neutron EDM plot. And your mass reach goes like 1 over the square root of the bound on the dipole moment. So if you can improve the bound by 2 orders of magnitude, you gain 1 order of magnitude in energy reach. This is scaling much faster than colliders, right? So you go here to here, that's 4 orders of magnitude, and that's 2 orders of magnitude and mass reach. Nobody has a proposal to make a collider go 2 orders of magnitude beyond where. And the standard model predicts these things to be very small. Okay, so I'm not going to linger on the details. I don't have time to explain. The standard model prediction is basically that you have to go at least 5 orders of magnitude beyond where they are now before you see an effect on the electron EDM, and there's similar stories for the hadronic EDMs like the nuclear moments. On the other hand, new physics can easily generate these things. All that you need is some interaction somewhere that has complex coefficient phase. That's generic. So here I've drawn a couple of Feynman diagrams. You can be a little more quantitative. This is diagrams that come from supersymmetry, but the scaling is very general. But one loop, you expect an electron EDM to go like electron mass divided by the mass scale of new heavy particle squared times this loop factor, Planck squared over 16 pi squared. You put in the numbers. If you can measure things at about the level they're measuring now, you're sensitive to new physics at about 100 TeV, 10 times beyond what any of the future colliders I've told you about could reach. The new physics appears at 2 loops. It can be even more generic. The 1 loop interactions kind of need something that talks specifically to the electron. The 2 loops, anything that interacts with electroweak gauge bosons and Higgs bosons can show up in this kind of diagram. And because it's a 2-loop diagram, it has more small numbers in front, but still, you're sensitive to kind of 5 to 10 TeV new physics if you can measure the kind of sensitivity people are measuring now. And just to show you that in a concrete model, this is work that I did a few years ago with some people who were my students at the time. They're postdocs now, Kerry Cesarati, Chen Chulu, and Jitya Parikh, and Yuichi Ronakai, who's a professor in Shanghai. We showed that at that time, the best electron EDM bound came from folks working at Harvard. It was slightly weaker than the current bound from the people in Boulder, but it was ruling out supersymmetric particles at something like 20 TeV. Again, a factor of 10 beyond the LHC. Now here's a very different kind of physics, lepton flavor violation. showed you earlier that a muon decays to an electron, but also with neutrinos that kind of make up for the flavor. We could ask, what if a muon decayed to an electron and a photon, and no neutrinos came out? We've had the muon flavor turn into the electron flavor, and we have violated lepton flavor. So that's what we call charged lepton flavor violation. There are many precision experiments looking for this muon decay to an electron and a photon, or for a muon scattering on a nucleus and turning into an electron. And this is a sort of a timeline. It's from a few years back. I don't have a more up-to-date version. But what they're showing is kind of over the next decade, there are realistic proposals to improve these constraints by orders of magnitude. If you look at the most optimistic ones from something like this PRISM experiment, it translates into probing new physics at around 50 TeV or higher. And 10 times what the LHC can do. There are precision experiments happening that are leaping beyond what these future colliders could do. And given that, people who do these experiments, some of my AMO colleagues to ask me, making dramatic progress. We're getting orders of magnitude in 5 years. We're talking about colliders that are decades down the road. Why? Why are you talking about colliders? Why don't we just keep doing precision experiments? We're much better at it than collider physicists. Precision experiments rule out all new physics at the 10 TeV scale. And the answer is no. We should take these experiments seriously. They are ruling out massive amounts of free space that you could think about. But there are principled theories that they don't rule out, at least yet. So one thing I thought about with some colleagues a few years back, this idea originally came from Yossi Nir and Ricardo Rotazzi 30 years ago, and we had sort of an updated look at it, was that maybe CP and flavor really are symmetries. We see that they're violated in the world around us, but maybe they're fundamental symmetries and they're spontaneously broken. They might be spontaneously broken in a correlated way. In the standard model, we only see CP violation at the same time that flavor violation is happening. We don't see them as independent processes. Maybe there's a deeper reason for that. And so then something like the electron EDM, which violates CP but not flavor, would be suppressed because it isn't bringing the two in the correlated way that we see in the standard model. And so we played with this. What we were doing at the time was trying to see if muon G-2, if the anomaly as it seemed to exist then, could be compatible with not having seen an electron EDM. Now muon G-2 doesn't seem to be an anomaly anymore, but take this as a proof of principle. We were asking, can there be new physics at the few hundred GeV scale that is not ruled out by these AMO experiments? And the answer was yes. In this kind of model, EDM happens to be small. It has extra small numbers in front. But it wasn't all that much small. It was 10 to the minus 30 e centimeters in this range. It was only a factor of 4 below the Gillow bound. So the lesson from this is that you can evade these things, but it's a non-trivial constraint on your theory if you want to evade them. And the further you want to push it, the harder you have to think about how to make a theory that does it. Okay, so getting toward the end of my time, let me just flash a few examples of recent work that I did. This was with Sam Haumiller, who's soon to be a professor at Pittsburgh, with Harvard student Jackie Lodman and my former student Aditya. We were thinking about the fact that there's this very general EDM, electron EDM, induced by new physics interacting with gauge bosons and Higgses. One thing a muon collider is really good at is studying interactions of gauge bosons and Higgses, so the muons can radiate W's. They can turn into Higgses. And so we could ask, can the same new physics that appeared here show up at a muon collider? That notice these parts of the diagrams inside the boxes look basically identical. They're related to each other by electroweak symmetry. So the idea was maybe if an electron EDM sees a signal, maybe a muon collider is the right experiment to actually unravel exactly what that signal is. Where did it come from? So what we showed is, because this thing is happening in a loop, there's something called the optical theorem that tells you if you hit a critical energy where you can cut the loop open, make the particles inside actual real particles instead of virtual particles, you get a feature in your rate. So that's this thing here. The imaginary part of the amplitude is 0 until you hit a critical energy, and then it's non-zero. There's a feature to look for. It's a small feature on top of a big standard model background. What we argued was that there is territory that is not yet ruled out by current EDM searches, that will be seen by future EDM searches, and where if you get a signal there, the muon collider will help figure out what the signal actually is. One more example along those lines. If we see lepton flavor violation, say we see muons decaying to electrons and photons, we know something violates lepton flavor, but we don't know what it is. Something else out there. What is it? One example of what it could be is supersymmetry with mixing between the supersymmetric partners of the muon and the electron. So with Sam Hollander and my former student Xianshu Liu, we looked at this a few years ago and showed that there's a collider signal you can look for, which is mu plus mu minus turning into mu plus e minus and missing momentum. The missing momentum is some invisible supersymmetric particles in the detector. What it looks like from the point of view of just looking at the leptons is, well, we had a muon coming in and we have an electron going out. Lepton flavor was by. You get much more from seeing it at a collider than you do from seeing it at mu to e gamma, because you can actually measure the energy spectrum of these things, and you can learn the mass of the particles involved and all kinds of details. And the red curve, these two plots, these are just two different sort of slices of parameter space. Everything above the red curve is accessible at a muon collider. Everything above this dashed green curve and this dashed green curve is accessible at kind of the next generation mu to e gamma experiment. We also put EDMs on here. So again, there are different assumptions on these two panels. One of them, current EDM bound, was ruling out this territory. This one, it was ruling out a larger piece of the territory. But the basic point is that all of these things, these EDM experiments and charged lepton flavor experiments that I was telling you are leaping way ahead of the LHC, they're leaping way ahead of the LHC if you sort of naively just translate them into mass reach. There's a lot of territory where they could be generated by physics at the several TeV scale that you could also see at a future 10 TeV parton center of mass collider, like a muon collider, like FCC-HH. And so there's a great opportunity for complementarity. You can hope to see signals in multiple experiments. And the main message I want you to take away is that if you only had the EDM experiments, or if you only had mu to e gamma experiments, you might learn that there's physics beyond the standard model, but you're not going to learn what it is. The best you can say is something is out there, its mass is below something, 30 TeV, but I don't know what it is. And colliders remain the only thing that we know where you can really pick apart a process, its energy dependence, see exactly what's going on, and measure many things at once, get kind of a multifaceted view of what that new physics really is in a way that can help you really build next standard model beyond what we have. Okay, so I've used up pretty much all of my time. I'm going to skip this one. I couldn't resist trying to sneak in a slide about axions because that's mostly what I'm thinking about, but you can ask me about it if you're curious. As I was just saying, colliders are the best option we have for really getting detailed information on physics at a particular energy scale. What I can't give you is a guarantee. We might build a 10 TeV collider, map out everything there is to see there, find that it's all the standard model. It could happen. There are finitely many unexplored orders of magnitude between the LHC and the scale of quantum gravity. Taking a leap into the unknown at high energies has paid off in the past. I think that it is a worthwhile thing for us to do to just go that next order of magnitude and see what's there. And there's also, I haven't talked much about it, but there's strong motivations for having new physics at that scale. Before the LHC, we talked a lot about electroweak symmetry breaking as the motivation for looking at this scale. I still think that's a good motivation. The fact that we've only seen the Higgs and nothing else at the LHC tells us that maybe electroweak symmetry breaking is slightly unnatural somehow. That doesn't mean that there's nothing for many orders of magnitude. It would still be more natural to have something showing up at 10 TeV than nothing until 10 to the 16 TeV. And the other thing I want to say is that I think these low energy experiments are beautiful and amazing. I love going to meetings with my AMO colleagues and hearing about all the things they can do. They're making really dramatic progress, and I really hope they make a discovery. But if they do, the immediate question I will ask, after we celebrate is, what did you actually discover? Right? We would now know there's something out there. We would know there's an EDM. What is it? The only way I know to answer that question is to build a collider. I think people sometimes portray these things as being opposed to each other. We have these competing ways of looking for new physics. But from my point of view, an EDM discovery would be the single best thing that could possibly happen for the field of colliders. Because then we could go to funding agencies and say, oh, we know. Something else is there, not very far away. Let's try to find out what it is. Higgs factories could make a discovery of new physics via precision. Then we would have a similar case. Something new is there. Let's find out what it is. But from my personal viewpoint, the territory they're probing looks a lot like the territory the LHC is already probing. So I'm more optimistic that precision coming from some other direction like AMO is going to find something new than precision coming from a Higgs factory. In any case, I think that we should build a new high-energy collider. I think that we should do it before we collectively forget how to. And so I I hope that there is some way that we can accelerate the timeline compared to some of the current models. I'll close there. Thank you.
Thanks for a fun talk, despite the lack of dinosaurs. Questions?
How does the cost of these new colliders compare with the cost of these large fusion projects?
Off the top of my head, I don't know. I mean, I guess the new colliders are roughly in the $10 billion ballpark. Maybe someone knows more precise numbers than I do. I don't know what the cost of large fusion projects is. Anybody have a better answer to that than I do?
During slow mass, we have extensive to estimate the cost. Like the muon collider roughly estimated 20 billion.
What did you say?
Muon collider roughly 20 billion.
8 billion. Uh-huh.
That's what the cost.
That's the order of magnitude. I mean, it's far enough out. I don't know how precise we can be. Okay. The statement, if you couldn't hear, was ITER is like 50 billion. Same order of magnitude, at least.
You said some less than nice things about a lepton collider or about a Higgs factory. So if you were running the show, would you, like at CERN, say, would you skip the EE machine and go straight to the HH machine?
Yeah, so let me repeat the question in case somebody didn't hear it. I guess the first was that I made some less than nice claims about Higgs factories, and if I were running the show at CERN, would we skip FCC-EE and do FCC-HH? I guess that's a hard question to answer, because one of the reasons FCC-HH follows FCC-EE is, again, that the magnet technology doesn't really exist yet. But there is the possibility of scaling back the scope a little bit and saying, I mean, it's already been scaled back. Originally it was 16 Tesla magnets, now it's 14. There's a possibility of saying, let's go for 12, or even some people recently said maybe we should go for just 8 Tesla magnets and aim for 50 TeV. No, luckily I'm not in charge of CERN, so I don't have to make these decisions. But I do think it's worth emphasizing that building high-energy hadron colliders is a thing that we know how to do. The obstructions are and cost, obviously, and the fact that you've got to either have a really big ring or really strong magnets. At CERN, you just can't go bigger than the size of the ring they can build. Maybe elsewhere in the world you could. So I don't know. Maybe the way I would phrase your question is if I had a multi-billionaire friend who wanted to build something, I would probably say, why don't we just build a really big hadron collider somewhere with magnets that we already have, just max out what we can do. But, you know, there are lots of constraints from politics and geography and everything, so I don't know.
There was a question
Over here, and then we'll go over that.
I also want to compliment you. You talk someone who here for the bias stuff and haven't heard about this thing for like 20 years. Something I could follow almost everything you tell. So thank you so much for keeping it accessible.
Thank you.
But on the question I was wondering again, I mean, I really follow a lot of sort of use of the sort of physics forefront, and I feel like the cosmology and cosmos radiation is kind of been the next frontier, and in terms of this discovering new physics of the high energy, I mean, you haven't talked about that side of experiments, and whether that, I mean, and again in the finite mining world, where you get better back to discover some of that in that energy scale by going into space and look at the cosmic rays and all that.
That's a great question, and let me go back to my slide early on. So the question was about going into space and doing cosmological observations and trying to access high energy that way instead of terrestrial particle physics experiments. And I do spend part of my time thinking about cosmology. I think that is an important way for us to try to go beyond the standard model. I'd say it's really going after mostly different questions, though. You know, the terrestrial experiments are sort of starting from this end and pushing out. Inflation is the most plausible theory we have of how the universe got its initial conditions. One of the things we've learned from inflation in terms of energy scales is that the Hubble scale during inflation was smaller than something. If it was bigger than that, there would be more primordial tensor modes, primordial gravitational waves, and we would have seen them in the CMB. So as those experiments improve, there's a line here that's pushing to the left. There's another set of ideas about using non-Gaussianities. Well, there was a colloquium here last week, for those of you who were around, by Misha Ivanov that told us about some of these ideas. Using non-Gaussianities to look for new heavy physics during inflation. That's another way to look for heavy things. It's sort of looking for things, again, that are probably somewhere in this high energy range. Although it's also worth keeping in mind that the mass of a particle during inflation may be different than the mass today. And so maybe some of the same particles we're looking for here were actually up there in the early universe because their mass is time dependent in some way. So it's a complicated question. I think there is a chance that we could first learn about physics beyond the standard model from that kind of observable. But it would be challenging to put it in the context of the standard model physics because it's sort of like some isolated piece of information up here. And it's hard to know how it connects to what we learn over here. It's also challenging, the things that are the cleanest, the most particle physics-like things you can do with cosmological observations are these cosmological collider signals. And they're really not going to reach their true power until we have like 21 centimeter mapped out three-dimensionally over a huge range of scales, many modes. So even there, a lot of it is further in the future. The near future things, they might tell us there was dark radiation. If they do, again, we wouldn't know what it is. We would just know there was something there. A lot of these things that we might get one number and would tell us something new is there, but it's hard to know what. So I'm enthusiastic about all of that stuff. I think we should be doing it, but I don't feel like any of it really competes with colliders in terms of their ability to, if something is there, really tell us precisely what it is and how it relates to what we already know.
Also, great talk. Thank you. Very clear. I understand that your focus is on beyond standard model, but your focus is also on the future of colliders. In the future of colliders, I was sort of surprised that you didn't mention things like the quark gluon plasma and all of the, QCD phase diagram and all the other things that we could look at in colliders that aren't, filling in the missing parts of the standard model per se, as far as fundamental particles. Do you want to comment on that as far as motivation for near-term colliders that could be useful for sharing with our funding colleagues in various
Yeah, I mean, right, so the question, again, if in case anyone didn't hear, was I focused on looking for things beyond the standard model, but there's a whole other set of things that happen at colliders, like the ion collisions and nuclear physics, electron-ion collisions, all these kinds of things. I don't know that I have a good answer to that, except to say that I personally don't work on those things. I've thought less about them. I don't feel like I have a super clear message. I mean, I think there's interesting physics happening there. It's just not my physics, and
nuclear physicists have gone all in on the electron-ion collider.
Just make a comment when you say before we collectively forget how to make colliders, like that is the bridge in the U.S. for the accelerator physics community is that they can make colliders.
I was going to ask a question. If you set aside all the politics and the funding and said, I want to build a Hadron Collider, thinking only about the constraints of geography and magnet technology, what would the parameters be? I mean, what would be sort of the sweet spot that we think could be achievable in a reasonable time in some place in the world, with the right geology and make that reasonable? What would be built?
yeah, that's an interesting question. I don't know that I have a precise answer to it. So the question is, if we set aside all constraints of politics and funding and just ask, what could we build technologically with the Hadron Collider? And certainly the LHC uses 8 Tesla magnets. I think it's not unreasonable to think 12 Tesla magnets are a thing we could use in the reasonably near future.
Well, we don't
Sorry, was there a Peter?
I was making a bit of a joke, but you could build 10 TeV click. And if you have a limited amount of money, there are things that we also know how to build lepton colliders.
Yeah, that's true. Yeah, right. So something like 10 TeV E plus E minus linear collider is a thing we could do. Yeah, I mean, I would think we could. I don't have a good sense of when the geographical and geological constraints of building a really big ring become intractable. But I don't.
We could build a 100-kilometer collider under Texas, and we could concrete super collider.
There's a partially dug tunnel.
Yeah. Years back, there was a kind of wacky proposal floating around for something called the collider in the sea that would sort of float in the Gulf of Mexico and
Gulf of America.
I mean, there's collider on the moon also.
Now I think. Oh, there's another question. So we've reached the stage where we need wine, but.
I'll be quick. So I think the earlier question was about the space. You know, we have cosmic rays which are very, very high energies. We know that there we detected them. And that is higher energy than LHC. So one can potentially study, you know, beyond the standard model with cosmic rays, or even active galactic nuclei or gamma ray bursts they're producing. They're also proton-proton collisions just in space.
That's right. Let me mention though that so the comment was there are high energy accelerators in space. There are high energy cosmic rays. There are active galactic nuclei. There are things producing high energy particles. But a lot of what we can do with those is more analogous to the fixed target experiments, right? Like a cosmic ray hits the Earth. The cosmic ray energy can be extremely high. The center of mass energy of its collision with something on Earth goes like the square root.
It's still higher than LHC.
It's still higher than LHC?
Yes.
Is?
Yes.
Not much higher, not like many orders of magnitude higher. And the luminosity is extremely low, right? The event rate is very low. So so far that does not seem to have been a good route, you know, in recent history to discover. Of course, in the early history of particle physics, a lot of things were discovered in cosmic rays.
So they have a detector on the ICC thing out there.
Detector on
the ICC. Called the ICC?
ISS. International Space Station. So on the International Space Station, there's the blanking on the name. Yes, AMS. Thank you. The AMS experiment. There are other things like the Fermi Gamma Ray Telescope. I mean, there are different ways we can look for high energy. I would say, you know, maybe the place where that comes closest to having an impact on particle physics is like indirect detection of dark matter. So imagining dark matter particles annihilating, but that's not the extreme high energy cosmic rays like you're talking about. So the extreme ones are out there and they're fascinating, but the event rate is so low that so far it doesn't seem like that's been a very promising way to learn about.
And the other thing is Dune. You know, Dune is one of the largest high energy experimental funded already project. And so this deep underground neutrino experiment will happen. And there's a lot of effort in that. And there will be search for beyond the standard model physics, clearly.
There's a lot of high intensity experiments, lower energy than I'm talking about, but high intensity, that are good ways of looking for particles that might not be at energy frontier, the highest mass, might be light things that weakly interact with us. Yeah, that's also important. It was just kind of orthogonal to most of what I was talking about in this talk, so I didn't mention that.
Any more last questions? Okay, we'll take one more and then we'll...
So I'm very curious about one thing. So you mentioned that Japan is going to impose mu crystals simply because mu plus is easier for them to handle, and they also would be able to handle E plus and E minus. So I'm just very curious, what is specific for mu minus that we have no control over?
Oh, you're asking why do they have positively charged muons and not negatively charged muons?
Yeah.
Do I know the answer to that off the top of my head?
Cooling. It doesn't matter. They make muonium. E minus, E plus.
Making muonium, okay. Maybe Patty should answer this question.
Oh, okay. I mean, I think the way they're cooling is they send the muons in, they bind up with electrons, and the electrons you have lying around the lab are all E minus. So they have to bind up E minus mu plus, and then they can eject the mu pluses from that bound state and have very low PT, and they can accelerate them. The point is all the electrons that are lying around are negatively charged.
It's also easier to make positively charged muons because you make protons hitting nuclei make positively charged.
So in principle, that's something guided by the fact that most of the particles that we directly have are particles instead of antiparticles.
In his talk. Oh, brings us full circle. Okay, Let's thank Matt again, and then we can go outside and have some tea.